January 16th, 1943, 11 p.m., Swan Island Shipyards, Portland, Oregon. The night did not feel like a precursor to history. It felt simply, brutally cold. On the banks of the Willamette River, the vast industrial sprawl of the Swan Island shipyards lay dormant under a winter moon that hung pale and indifferent over the black water, casting long, skeletal shadows through the latticework of the cranes and gantries that dominated the skyline. Usually, this place was a cathedral of noise, a relentless, 24-hour cacophony of pneumatic riveting guns, the hiss of arc welders, the shouting of foremen, and the grinding of steel against steel that served as the soundtrack to the American war effort. But it was late on a Saturday night, and the frantic tempo of production had paused for the shift change, leaving the docks wrapped in a heavy, unnatural silence that was broken only by the groaning of the mooring lines and the slap of the river water against the pilings. The temperature had been dropping steadily since sunset, plunging past the freezing point and settling into a bitter 26 degrees Fahrenheit, a damp, penetrating Pacific Northwest frost that coated the iron railings in white rime and made the air feel like a physical weight in the lungs. Resting at the outfitting dock, dominating the view with her sheer mass, was the SS Schenectady. She was magnificent, a 500-foot-long monolith of gray steel that represented the absolute pinnacle of modern naval engineering. She was the very first of the new T2 SEA-1 tankers, a new breed of supership designed to carry 140,000 barrels of volley, aviation fuel, and diesel across the dangerous oceans to the desperate armies fighting in Europe and the Pacific. To the men who walked her decks, she didn't just smell like paint and wet rope. She smelled of victory. She was brand new, having returned from her sea trials only hours earlier, where she had performed flawlessly, cutting through the river currents with a grace that belied her 10,000-ton displacement. The Navy inspectors had walked her length, checked her pumps, tested her steering gear, and signed the acceptance papers with the confidence of men who believed they were looking at the future of maritime warfare. The night watchman, bundled into a heavy wool coat and stamping his feet on the steel deck to keep the blood flowing in his toes, felt a sense of security standing on something so solid. The ship felt immovable, a man-made island of iron that was tied securely to the pier, her cargo tanks empty and echoing, her hull resting high in the calm water. There were no storms here. There were no German U-boat wolf packs prowling beneath the surface. There were no Japanese dive bombers screaming out of the clouds. There was only the quiet river, the frost, and the sleeping city of Portland across the water. But the watchman was standing on a lie. Beneath the fresh coat of gray paint, deep within the atomic structure of the hull plates, a silent war was raging that no human eye could see. The ship was fighting a battle against herself, a struggle between the millions of pounds of tension locked into her welded seams and the freezing temperature that was slowly robbing the steel of its will to survive. The metal was contracting, pulling tight against the rigid frames, screaming in a frequency that was too high for ears to hear, but which was vibrating through the molecules of the vessel like a violin string tightened until it was ready to snap. At exactly 11:03 p.m., the physics finally gave way. It did not begin with a warning groan. It did not start with the slow, tearing sound of metal fatigue that usually precedes a structural failure. It arrived with the violence of a thunderclap. A single deafening boom shattered the silence of the shipyard, a sound so loud, so sharp, and so percussive that it was heard miles away in the sleeping suburbs of Portland. It was a report that sounded indistinguishable from a heavy artillery shell detonating at point-blank range. A sonic shockwave that rattled windows, set dogs barking across the city, and knocked the terrified watchman off his feet onto the frosted deck plates. On the pier, the skeleton crew of maintenance workers threw themselves to the frozen ground, covering their heads with their hands, their minds instantly racing to the darkest possibilities of wartime. In the paranoid atmosphere of 1943, There was only one explanation for an explosion of that magnitude. The war had come to Oregon. They waited for the second blast, for the whistle of falling bombs, or for the chatter of machine gun fire from a Japanese submarine surfacing in the river. But there was no second explosion. There was no fire. There was no smoke rising into the night sky. As the workers scrambled to their feet and the shipyard sirens began to wail, their beams of light cutting through the icy mist to find the source of the attack, they saw something that their brains refused to process. The Schenectady was not sinking. She was breaking. Right before their horrified eyes, a massive ship, still tied securely to the dock, began to transform. A crack had appeared on the deck just after the bridge superstructure, but crack was too small a word for the chasm that was opening. It ran instantly from the starboard rail to the port rail, severing the heavy steel plating as easily as a child tearing a piece of paper. With a horrific screeching sound of torturing metal that drowned out the sirens, the ship jackknifed. The sheer weight of the unsupported hull caused the center of the vessel to rise nearly 10 feet into the air, arching its back like a dying animal in a final spasm of agony. The bow and the stern, no longer held together by the strength of the deck, plunged downward into the river mud, sending massive waves washing over the pier. The violence of the event was absolute. Heavy steel cables, pulled beyond their breaking point, snapped with the sound of whip cracks, lashing across the dock with enough force to cut a man in half. Steam pipes ruptured, sending blinding white clouds hissing into the freezing darkness. Hydraulic lines burst, spraying fluid over the wreckage. The gangway was torn from its mountings and swallowed by the dark water. In less than 60 seconds, the transformation was complete. The most advanced ship in the United States Navy, the pride of the Kaiser Empire, the vessel that was supposed to save the free world, sat broken in the mud of the Willamette River. She was dead. Her back was broken. The gap in her deck was wide enough to drive a truck through, a jagged wound that exposed her ribs and framing to the cold night air. The lights of the emergency vehicles began to flood the scene, reflecting off the shattered steel and the white steam. Men were running, shouting orders, checking for casualties, their voices thick with panic and confusion. Sabotage. Someone screamed. Check the waterline. They've mined the keel. Get the FBI. Get the Navy. But as the chaos swirled around the wreck, the ship itself lay silent. She had not been destroyed by a torpedo. She had not been destroyed by a bomb. She had destroyed herself. This is the story of an engineering nightmare that almost lost the Second World War. It is a story not of spies and soldiers, but of molecules and temperature. It is the story of how a flaw smaller than a fingernail brought down a giant, and how the death of this one ship forced humanity to rewrite the laws of physics. If you are fascinated by the hidden disasters that shape the modern world, by the forensic hunt for truth inside twisted metal, and by the stories of engineering that usually go untold, make sure to hit that subscribe button and turn on notifications. You are about to discover why the steel that surrounds you every day is only safe because of what happened on this freezing night in 1943. The FBI agents were already racing toward the shipyard, their sirens screaming, their revolvers drawn, ready to hunt for a German saboteur in the shadows of the cranes. But they were running toward the wrong enemy. The killer was already gone, hidden in the grain of the metal, leaving behind a mystery that would terrify the War Department and threaten to turn the entire Allied fleet into glass coffins. January 17th, 1943. Dawn, Portland, Oregon. When the sun finally clawed its way over the Cascade Mountains, it illuminated a scene that looked less like an industrial accident and more like the aftermath of a Caillou attack. The fog that hung over the Willamette River was thick and gray, swirling around the twisted wreckage of the Schenectady like a shroud. In the harsh light of morning, the catastrophe was even more impossible to comprehend than it had been in the darkness. The ship was a ruin. The midship section was jackknifed so high out of the water that you could see the barnacles on the keel, while the bow and stern were buried deep in the river mud, giving the vessel the appearance of a giant steel bridge that had collapsed under its own weight. The shipyard, usually a hive of organized chaos, was locked down tight. The gates were barred. Armed military police patrolled the perimeter, their breath pluming in the freezing air, their eyes scanning the crowds of confused workers who had gathered to gawk at the corpse of the supertanker. But the men moving with the most purpose across the frosted pier were not the welders or the foremen. They were men in heavy wool overcoats and fedoras, stepping out of black government sedans with the grim determination of inquisitors. The Federal Bureau of Investigation had arrived. To the agents on the ground, and to J. Edgar Hoover back in Washington, the equation was simple. A brand new ship, a critical asset for the war effort, did not simply break in half while tied to a dock. Steel was strong. American engineering was infallible. Therefore, the destruction of the Schenectady had to be an act of malice. It was the only explanation that made sense in the paranoid fever dream of 1943. The agents swarmed the facility, treating the shattered hull as a crime scene. They pulled the night watchman into a cramped office, grilling him for hours about strange lights, small boats approaching from the river, or accents he might have heard in the shadows. They seized the employment records of the shipyard, hunting for names that sounded too German, or histories that hinted at labor radicalism. They were looking for the fifth column, the invisible army of saboteurs that every propaganda poster warned was hiding in America's factories. But while the FBI hunted for a phantom bomber, the true stakes of the disaster were being calculated in the war rooms of the Pentagon and the British Admiralty. To understand why the death of this one ship sent a shiver of terror through the highest levels of the Allied command, you have to look away from Portland and gaze out at the terrifying expanse of the North Atlantic. The war was hanging by a thread, and that thread was made of steel tonnage. In early 1943, the Allies were losing the Battle of the Atlantic. German U-boat Wolf Packs were operating with impunity, sinking merchant ships faster than the United States and Britain could replace them. The ocean floor was littered with the carcasses of freighters carrying wheat, tanks, and ammunition. The strategy of the Axis powers was brutal and effective: starve the island of Great Britain and cut off the supply line to the Soviet Union. If the ships stopped sailing, the planes in England would run out of fuel, the people would starve, and the invasion of Europe Operation Overlord would be impossible before it even began. The American answer to this existential threat was the greatest industrial gamble in history. It was a concept called the Bridge of Steel. The architect of this bridge was Henry J. Kaiser, a man who built ships the way Henry Ford built cars. Kaiser realized that the old way of shipbuilding, the way of the craftsman, was dead. Before the war, a ship was a bespoke creation, painstakingly riveted together, plate by plate, by men who had spent decades learning their trade. It was a slow, rhythmic, noisy process that produced sturdy, flexible vessels, but it took months to launch a single hull. Kaiser didn't have months. He had days. He revolutionized the industry by betting everything on a relatively new technology: electric arc welding. He stripped the art out of shipbuilding and replaced it with pure speed. In his massive new yards, like the one at Swan Island, ships were not built, they were assembled. Enormous sections of the hull, weighing tens of tons, were prefabricated in fields miles away from the water. They were trucked to the slipways and lifted into place by giant cranes. Then, an army of workers, many of them women, the famous Rosie the Riveters, though in this case they were Winnie the Welders, would fuse the sections together with lightning. Welding was faster. It was lighter, saving tons of weight that could be used for cargo. It was cheaper. It allowed the United States to launch ships at a rate that Hitler's strategists declared was mathematically impossible. The Liberty ships, and now the massive T-2 tankers, were streaming out of American ports. A flood of gray steel that was supposed to overwhelm the U-boats by sheer numbers. The Schenectady was the prototype of this victory. She was the proof that the new way worked. She was the first of the T2 South, bigger, faster, and more complex than the Liberty ships. She was designed to carry the high-octane aviation fuel that the heavy bombers needed to flatten Berlin. But as she lay broken in the Willamette River, she became a symbol of something else entirely. She became a confirmation of the darkest fears held by the old-school naval architects who had whispered against Kaiser's revolution. There had always been skeptics. The riveters had warned that welded ships were too rigid. They warned that welding was a violent process that traumatized the metal. They warned that in the rush for speed, quality was being sacrificed. But they had been silenced by the desperate need for tonnage. Now, with the Schenectady destroyed, those whispers turned into a roar. If the flagship of the welding revolution could snap in half in calm water, what would happen to the hundreds of other welded ships currently battling the 40-foot waves of the North Atlantic? Back at the crime scene, the investigation was hitting a wall. The FBI agents, frustrated and exhausted, were finding nothing. There were no traces of dynamite residue on the torn steel. There were no fragments of a timer. There were no witness accounts of a saboteur running from the scene. The hull plates bent outward and inward in chaotic ways, but there was no signature blooming effect that comes from a high explosive charge detonating against the keel. The saboteur theory was evaporating, and as the possibility of human malice faded, a much more terrifying reality began to take its place. A team of engineers from the U.S. Maritime Commission and the American Bureau of Shipping finally gained access to the wreck. These were not policemen. They were scientists of steel. They climbed over the frosted railings, their breath misting in the cold air, and walked right up to the edge of the abyss, a fracture line that ran across the deck. They knelt down on the icy steel, ignoring the FBI agents who were still searching the bilges for bombs. They ran their gloved fingers over the face of the break. In a normal shipwreck, caused by a collision or a torpedo, steel behaves in a predictable way. It fights back. It twists, it stretches. It thins out like pulled taffy before it finally tears. It leaves behind a rough, fibrous surface that tells the story of a violent struggle against physics. But the steel of the Schenectady looked wrong. The face of the fracture was not rough or twisted. It was terrifyingly clean. It sparkled in the winter sunlight with a granular, crystalline texture. It looked sharp enough to shave with. It didn't look like metal that had been torn. It looked like a piece of glass that had been dropped on a stone floor. The head engineer looked at his colleagues, and the color drained from his face. He realized that they weren't dealing with a bomb. They were dealing with a fundamental betrayal of the material itself. The ship hadn't been murdered by a German spy. It had been murdered by the cold and by a ghost hidden inside the atoms of the fleet. And the most frightening thought was not that the Schenectady was unique, but that she was exactly like every other ship currently sailing to war. January 17th, 1943. Midday. The deck of the SS Schenectady. The FBI agents eventually holstered their weapons and retreated to their sedans. Their theories of German saboteurs dismantled not by an alibi, but by the steel itself. The investigation now belonged to a different kind of detective, the metallurgists. Standing on the wind-whipped deck of the broken tanker, looking down into the icy water of the Willamette River through the 5-foot gap in the hull, was a team led by the country's top naval experts. They were there to perform an autopsy, but unlike a medical examiner who looks for a bullet hole or a poison, these men were looking for a roadmap written in the grain of the metal. They knew that a brittle fracture leaves a signature. When steel snaps like glass, the energy of the break travels at thousands of miles per hour, but it leaves behind microscopic tracks faint, chevron-shaped ridges that point back against the flow of the crack. They look like arrows on a hiking trail, all pointing in one direction. The crack came from over there. The engineers began to walk the length of the fracture, moving from the port side, across the deck, toward the starboard rail. They were tracking the beast back to its lair. They followed the arrows across the center line. They followed them past the twisted piping. They followed them to the heavy steel plating of the starboard side hull, the sheer strake. This was the thickest, strongest band of steel on the ship, the rim that held the vessel's shape. And there, deep in a welded seam connecting two massive plates, the arrows stopped. The lead investigator leaned in close, his magnifying glass hovering inches from the jagged edge. The wind bit at his exposed face, but his hand was steady. He was looking at the origin point of a disaster that had cost millions of dollars. He found it. It wasn't traumatic. It wasn't a gaping hole. It was a tiny, grayish, non-metallic speck trapped inside the solidified steel of the weld. It was no bigger than a grain of rice. It was a slag inclusion. To the uninitiated, it looked like a bit of dirt. But to the engineer, it was the smoking gun. It told a complete, tragic story of human error and industrial haste. Weeks earlier, somewhere in this very shipyard, a welder had been working on this seam. It was likely the graveyard shift. The lights were glaring, the air was filled with toxic smoke, and the foreman was yelling about quotas. The welder was tired. He was moving too fast. When you weld with an electric arc, the flux coating on the rod melts to form a protective shield over the molten metal. This waste material, called slag, hardens quickly. A careful welder chips it away with a hammer before making the next pass. But this welder had missed a spot. He had laid a bead of fresh, molten steel right over a piece of hardened slag. He had buried a bubble of impurity inside the ship's skin. On the surface, the weld looked perfect. The paint covered it. The inspectors walked right past it. But deep inside the molecular lattice of the Schenectady, that tiny bubble was a void. It was a nothingness. And in the world of high-stress physics, nothing is the most dangerous thing there is. This discovery unlocked the terrifying physics of the collapse. The engineers realized that the Schenectady had been fighting a civil war since the moment she was launched. It was a concept called residual stress. When Henry Kaiser's army of workers welded these massive ships together, they were using heat thousands of degrees of it. When hot metal cools, it shrinks. On a ship as vast as the Schenectady, with miles of welded seams, its shrinkage was catastrophic. The cooling welds were pulling on the steel plates with millions of pounds of force. A deck was trying to shrink, but the hull was rigid. The ship was essentially a giant, 10,000-ton drum skin, pulled so tight it was screaming. For weeks the steel had held that tension. It was strong enough to resist the pull. But then came the night of January 16th. The temperature dropped to 26 degrees. The thermal stress of the cold added even more tension to the already tortured metal. Simultaneously, the cold triggered that deadly ductile to brittle transition. The steel lost its ability to stretch. It turned stubborn. It turned into glass. All that massive pent-up energy needed a place to escape. It started looking for a weakness. It scanned the millions of inches of steel in the hull, testing every plate, every rivet, every beam. It found the welder's mistake. That tiny grain of slag acted as a stress concentrator. Think of trying to tear a bag of potato chips. You can pull on the plastic all day, and it won't rip. But if you make a tiny nick in the edge with your teeth, the bag tears effortlessly. The slag inclusion was the nick. At 11:03 p.m., the stress at the tip of that tiny bubble exceeded the strength of the brittle steel. Snap! The energy was released. The crack launched out of the flaw at the speed of sound, unzipping the ship before the sound of the break could even reach the watchman's ears. The mystery of the Schenectady was solved. But the solution brought no relief. In fact, it brought a wave of nausea to the men standing on the deck. If this was caused by a random welder's error, combined with the standard welding practices used in every shipyard in America, then the Schenectady wasn't an anomaly. She was the norm. There were hundreds of Liberty ships and T-2 tankers already at sea. They were built by the same tired welders. They were made of the same cold-sensitive steel. They were held together by the same tension-filled welds. And they were sailing into the North Atlantic winter. As the engineers packed up their tools, reports began to filter in from Navy intelligence that had previously been dismissed as rumors or bad luck. The SS Valery Chilov, a Liberty ship given to the Soviets, had broken in two in the North Pacific. The SSSO Manhattan had split in half entering New York Harbor on a calm day. There were dark whispers of ships disappearing in the mid-Atlantic gaps, vanishing without sending an SOS, with no U-boats in the area. The pattern was undeniable. The United States had built a bridge of steel to save Europe, but they had unknowingly built it out of glass. They had sent thousands of merchant mariners to war in vessels that were liable to disintegrate if the weather got too cold. The War Department was facing a nightmare scenario. They couldn't recall the fleet. The Allies would starve. They couldn't stop building welded ships. The war would be lost. They had to find a way to fix a microscopic flaw hidden in millions of tons of steel. And they had to do it while the ships were fighting a war. The order came down from the highest levels of the government. Find a cure, and find it now. February 1943. The North Atlantic convoy routes. While the engineers in Portland were peering through magnifying glasses at grains of slag, the horror of their discovery was already manifesting in the freezing darkness of the mid-Atlantic gap. To the men of the Merchant Marine, the news of the Schenectady didn't arrive as a scientific report. It arrived as a rumor, whispered in the mess decks, and shouted over the roar of the wind. They began to look at their own ships differently. They were sailing on the T-2 tankers and the Liberty ships, the identical gray boxes that formed the lifeline to Europe. They had always feared the external threats, the periscope feathering the water, the shadow of a Focke-Wulf condor in the clouds, the drifting naval mine. But now they began to fear the ship itself. The sailors christened them with a dark new nickname, Kaiser's Coffins. Every time the temperature dropped, every time the hull groaned in a heavy swell, the crews held their breath. They knew that beneath their feet, the steel was reacting to the cold. They knew that the molecular lattice was locking up, turning brittle, and that a microscopic crack could be racing toward them faster than the speed of human thought. The reports that reached the British Admiralty and the U.S. War Department were suppressed from the newspapers to prevent public panic, but they were terrifying in their frequency. Ships were arriving in Liverpool and Murmansk with massive fractures in their decks, held together only by luck and the heavy keel plates. Captains reported sounds like gunshots ringing out in the night, only to find daylight shining through the main deck the next morning. In Washington, the situation was viewed with a quiet, desperate terror. The invasion of Europe was being planned. The tanks in North Africa needed gasoline. The Soviet Union was screaming for supplies. The bridge of steel could not be closed. The engineers at the Maritime Commission were tasked with solving an impossible riddle. How do you stop a crack that moves through a solid block of metal at 11,000 miles per hour? They sat in smoke-filled rooms, staring at blueprints of the T-2 tankers. They couldn't simply make the steel tougher. The steel mills were already running at maximum capacity, producing armor plate for tanks and battleships. They couldn't go back to riveting every ship. It took too long and required skilled labor that didn't exist. They couldn't keep the ships in warm water. The war was in the cold. They had to find a way to fix a problem that was baked into the very atoms of the fleet, and they had to do it while the ships were active, loaded with explosive fuel, and fighting a war. The solution, when it finally emerged, was a humbling admission of defeat for the new technology. To save the welded ships, the engineers realized they had to look backward. They had to return to the very method Henry Kaiser had tried to eliminate: the rivet. The logic was based on the behavior of the crack itself. In a welded ship, The hull is a monolith, a single continuous sheet of steel from bow to stern. A crack in a welded hull is like a forest fire in a dense, unbroken wood. It burns until it consumes everything. There is no gap to stop it. But if you cut a gap in the forest fire break, the flames hit the dirt and die. The engineers proposed a radical, violent surgery for the entire fleet. They called it the crack arrestor. The order went out to shipyards across the world, from Brooklyn to Halifax, from Glasgow to Pearl Harbor. It was a counterintuitive instruction that confused the workers. They were told to take their cutting torches and deliberately slice massive slits into the hulls and decks of these brand new ships. They were ordered to wound the vessels they had just built. They cut long, longitudinal slots through the deck plating and the sheer strake, severing the perfect welded seams that Kaiser had been so proud of. Then, over these artificial wounds, they placed heavy steel straps. But they didn't weld them. They drilled holes, thousands of holes, and they hammered in rivets. It was an iron stitch, a heavy, ugly, mechanical bandage wrapped around the hull of the ship. The theory was simple but brilliant. When the lethal crack launched out of a flaw like the one in the Schenectady, tearing through the brittle welded steel, it would eventually hit the slot. The energy of the fracture would try to jump across to the strap, but the strap wasn't welded. It was riveted. It was mechanically separate. The continuity of the metal was broken. The crack would race into the slot, hit the empty space of the rivet hole, and have nowhere to go. Its energy would dissipate. It would die. It was a frantic, global retrofitting operation. Ships were pulled out of convoys and rushed into dry docks. They were swarmed by workers who cut and drilled with the desperation of field surgeons trying to stop a hemorrhage. The sleek, smooth lines of the T2 tankers were broken by these crude, heavy straps. They looked scarred. They looked like brawlers who had been stitched up in a back alley. But the question remained, would it actually work? Theory is one thing. The North Atlantic is another. The engineers had done the math, but they hadn't tested it in the real world. They needed a ship to go out into the freezing gales, take a hit, and survive. That test came in March 1943 on a lonely stretch of ocean south of the Aleutian Islands. The SS Sackett's Harbor was a sister ship to the Schenectady. She was a T2 tanker, built in the same yards, welded by the same men, made of the same cold-sensitive steel. She was plowing through heavy gray rollers, her tanks full of fuel for the forces fighting the Japanese in the Aleutians. The air temperature was freezing. The water was 34 degrees. Deep in her deck plating, a flaw woke up. The stress overwhelmed the brittle steel. The familiar, terrifying gunshot sound rang out across the water, deafening the crew on the bridge. A massive crack ripped open in the center of the ship, tearing through the steel walkway, slicing through the piping, and racing toward the edge of the hull. It was the Schenectady disaster all over again. The crew braced themselves for the ship to jackknife, for the bow to plunge into the sea, for the freezing oil to swallow them. But the ship didn't break. The crack raced across the deck and slammed into a heavy steel hatch, combing a reinforced ring of metal that acted exactly like a crack arrestor. It hit the discontinuity. It hit the rivets, and it stopped. The ship groaned. The deck heaved in the swell. The crack breathed, opening and closing with the waves, a terrifying mouth in the steel. But it didn't grow. The iron stitch held the skin together. The Sackett's Harbor limped back to port, battered and terrified, but afloat. When the engineers examined her, they saw the proof. The crack had been stopped inches from total destruction. The Band-Aid had worked. The crisis was contained. The glass fleet was slowly being transformed back into a fleet of iron. But back in Portland, the corpse of the Schenectady still lay in the mud. The engineers weren't done with her yet. They were about to attempt a resurrection that would prove to the world that a broken bone could be stronger than the original limb. March 1943. The Willamette River Portland. For 2 months, the corpse of the SS Schenectady had been a fixture of the Portland waterfront, a grim tourist attraction for the shipyard workers who glanced nervously at her broken back as they clocked in for their shifts. She lay deep in the river mud, a twisted monument to industrial hubris. To the casual observer, she was a total loss, a $10 million pile of scrap metal that would inevitably be cut apart with torches and fed back into the smelters to build tanks or jeeps. The gap in her deck was still a gaping wound. The keel was bent at a violent angle, and the interior compartments were flooded with the filth of the river bottom. But inside the offices of the U.S. Maritime Commission, a different calculation was being made. The war was consuming tankers at a rate that terrified the strategists. Every week, U-boats sent thousands of tons of shipping to the bottom of the Atlantic. The shipyards were launching new hulls as fast as they could, but it wasn't enough. The Allies were starving for tonnage. They couldn't afford to throw away a ship that was 90% complete just because she had snapped in the middle. The order came down to perform the most audacious surgical operation in the history of naval engineering. They were not going to scrap the Schenectady. They were going to heal her. The operation began with brute force. They didn't have the time or the facilities to drag the massive wreck into a dry dock, so they decided to fix her right there in the river. Teams of divers descended into the freezing, murky water, blindingly groping in the mud to slide massive steel girders under the broken keel. On the deck, they positioned hydraulic jacks capable of lifting locomotives, chaining them to the twisted frames of the fracture. It was a delicate, violent ballet of physics. Slowly, inch by agonizing inch, the pressure was applied. The ship groaned. The metal screeched as the twisted plates were forced back into alignment against their will. It was the industrial equivalent of setting a compound fracture on a giant's leg. The workers on the pier watched in silence as the 5-foot chasm in the deck began to close. The jagged teeth of the steel bit back together. Finally, with a deep, resonant clang that vibrated through the hull, the two halves of the Schenectady kissed. The ship was whole again. But the engineers knew that simply welding her back together would only recreate the bomb that had gone off in January. They had to change her DNA. They swarmed the hull with the new knowledge they had gained from her death. They applied the iron stitch. Workers burned the slots for the crack arresters and hammered in the heavy riveted straps that would act as the fire breaks for any future cracks. They reinforced the shear strake with massive bands of steel. They heated the hull to relieve the residual stress, relaxing the tension that had torn her apart. When the work was done, the Schenectady was no longer the sleek, smooth-skinned beauty that had launched in January. She was scarred. She was covered in patches, heavy rivets, and thick steel straps that ran along her length like surgical sutures. She looked like a Frankenstein's monster, a brawler who had been stitched up in a back alley and pushed back into the ring. April 1943. The resurrection. The true test of the Schenectady was not whether she could float. It was whether men would sail her. Sailors are a notoriously superstitious breed. To a mariner, a ship is a living thing, and a ship that breaks its back before its maiden voyage is cursed. It is a bad luck boat, a vessel marked by death. When the call went out to assemble a crew for the resurrected tanker, there were whispers along the waterfronts of the West Coast. Who would be crazy enough to sign on to the ship that snapped? But the war had a way of overriding superstition. A crew was assembled, a mix of old salts and young recruits who grabbed their sea bags and walked up the new gangway. They stepped onto the deck, their boots ringing on the steel that had failed 3 months earlier. They looked at the massive riveted straps that covered the scar. They slept in bunks that had been underwater weeks before. There was a nervous energy on board, a sense that they were riding a ghost. In late April, the lines were cast off. The tugboats pulled the Schenectady away from the dock that had almost been her grave. She turned her bow the same bow that had plunged into the river downstream toward the ocean. To reach the Pacific, she had to cross the Columbia River bar. It is known as the graveyard of the Pacific, a chaotic convergence of river current and ocean swell that creates some of the most violent waves on Earth. This was the ultimate test. If the Schenectady was going to break again, she would do it here. As the ship hit the first massive rollers of the Pacific, the bow rose and the stern dropped. The hull flexed. The sailors on the bridge gripped the railings, their knuckles white. They waited for the gunshot sound. They waited for the deck to open up and swallow them. They waited for the scream of tearing metal. But the sound never came. The rivets held. The steel stretched. The crack arresters stood guard, silent sentinels absorbing the stress of the ocean. The ship rode up the waves and crashed down into the troughs, groaning not in pain, but in effort. She punched through the swell and reached the open sea, her engines humming a steady rhythm of defiance. The curse was broken. For the next 2 years, the ship that was supposed to be a failure became a legend of endurance. She didn't just survive. She went on the offensive. She was assigned to the Pacific Theater, becoming a vital link in the floating pipeline that fueled the U.S. Navy's relentless island-hopping campaign. She carried aviation fuel to Pearl Harbor. She steamed into the humid, typhoon-prone waters of the Marshall Islands. She fueled the aircraft carriers that struck Truk Lagoon and the destroyers that hunted Japanese submarines. While other Liberty ships and tankers were still struggling with fractures, until they too could be retrofitted, the Schenectady kept plowing through the waves. She survived the tropical heat that expanded her steel and the sudden squalls that cooled it. She dodged torpedoes and kamikazes. The crew's fear slowly turned into a fierce pride. They stopped calling her a bad luck boat. They started calling her the Lucky Shen. They bragged in port bars that they sailed on the ship that couldn't be killed. They claimed that because she had already broken in half once, she had gotten it out of her system. She was the toughest ship in the fleet because she had already died and come back to life. She sailed until the very end. She was there when the Japanese Empire crumbled. She outlived the war that created her. It wasn't until 1948, after hundreds of thousands of miles of service, that she was finally retired. She was sold to a shipbreaker in Italy, not because she was broken, but because she was obsolete. As the workers in Genoa finally cut her apart with torches, they found that the repair welds were still perfect. The iron stitch had never failed. The broken bone, once healed, had indeed been stronger than the original limb. But while the steel of the Schenectady was melted down to build the post-war world, her ghost was about to do something even more important. The lessons learned from her autopsy were moving from the shipyards to the laboratories, birthing a new science that would save millions of lives in the future. The Schenectady was gone, but her legacy was just beginning. 1948, Genoa, Italy. The end of the SS Schenectady was quiet. There were no explosions, no snapping steel, no sirens. Just the hiss of a cutting torch in a sun-drenched Italian scrapyard. After surviving the war and carrying millions of gallons of fuel across the Pacific, the ship that had terrified the Pentagon was finally dismantled. Her massive steel plates were cut into sections, melted down in a furnace, and reborn. The metal that had once formed the hull of the glass ship became rebar for new buildings, panels for Fiat cars, or girders for bridges in a rebuilding Europe. The physical ship was gone, but in a way that is rare in the history of machines, the Schenectady achieved immortality. She didn't leave behind a wreck to be visited by divers. She left behind a question that haunts every engineer to this day. Before that freezing night in Portland, the world of engineering was built on a dangerous assumption, the assumption of perfection. Architects designed bridges, planes, and ships as if the materials they used were flawless. They calculated static strength, asking simply, is this beam thick enough to hold this weight? The Schenectady proved that was the wrong question. She taught humanity that perfection is a myth. She proved that every piece of metal, no matter how carefully forged, contains a ghost, a microscopic bubble, a tiny scratch, a hidden inclusion like the one that killed her. You cannot eliminate the flaws. You can only learn to live with them. From the wreckage of the Schenectady, a new branch of physics was born, fracture mechanics. It is the science of the crack. It is the mathematical understanding of how energy travels through a material, and crucially, how to stop it. It shifted the philosophy of building the world from strength to tolerance. The echo in the laboratory today. In metallurgical laboratories around the globe, the ghost of the Schenectady is summoned every single day. Engineers perform a standard procedure called the Charpy V notch test. They take a small bar of steel and cut a tiny, precise V-shaped notch into it, a deliberate flaw that mimics the welder's mistake of 1943. Then they freeze the steel to sub-zero temperatures, recreating the bitter Portland night. Finally, they drop a massive pendulum hammer. The hammer strikes the sample. If the steel snaps cleanly, like glass absorbing very little energy, it is rejected. It is brittle. If it tears, bends, and hangs on absorbing the blow like taffy, it is accepted. It is tough. This test, the gold standard for safety, exists largely because we learned the hard way that steel has a transition temperature. Every time a batch of steel passes this test, it is because the Schenectady failed it first. But the most profound legacy of the glass ship is not found in the water. It is found 30,000 feet above our heads. Every time you step onto a modern jetliner, you are trusting your life to the lessons learned on the Willamette River. An airplane fuselage is, in essence, a pressurized metal tube that expands and contracts with every flight. It endures the freezing cold of the stratosphere and the heat of the tarmac. It is a structure under immense tension, fighting against fatigue, the exact same environment that snapped the tanker. If you look closely at the skin of an aircraft or the design of the window frames, you are looking at the great-grandchildren of the N stitch. Modern planes are designed with tear stoppers, bands of thicker metal or composite material that run around the fuselage. If a fatigue crack starts, and engineers assume it will start, it races through the skin until it hits a tear stopper. Then, just like on the Sackett's Harbor, it stops. It is contained. The plane doesn't unzip. It lands safely. The verdict history is often unkind to failures. We remember the ships that were sunk by enemy fire. The Arizona, the Bismarck, the Hood. We build monuments to the battles and the tragedies. But we rarely remember the ships that were killed by physics. The SS Schenectady was an unsung martyr of the industrial age. She wasn't sacrificed to a torpedo or a bomb. She was sacrificed to our own ignorance. Her destruction was the tuition fee humanity had to pay to enter the modern era of high-stress engineering. If she hadn't snapped that night in the quiet safety of the Portland harbor, if she had sailed into the North Atlantic and broken apart in a storm with her crew on board, the mystery might have been buried at sea. The flaw might have gone undetected for months longer. Dozens more ships might have been lost. Thousands more sailors might have drowned in the freezing oil of the Atlantic, victims of a science we didn't yet understand. The glass ship broke so that the world could learn to bend. Today, the steel that surrounds us in the bridges we cross, the pipelines that heat our homes, and the planes that carry us across oceans, is safer, tougher, and more resilient. And deep in the grain of that metal, if you know where to look, you can still find the invisible scar left by the ship that split in half, and in doing so, helped hold the modern world together.